Now move on to the second part of the webinar, where we have presentations by experts from leading companies, members of COGEN World Coalition. So I'd like to invite the first panelist, or speaker, I should say. I'm very pleased to invite Alex Marshall, who is the Group Business Development and Marketing Director in the US for Clarke Energy. So the floor is yours, Alex. We're looking forward to your presentation.
Thank you very much, Hans. I'm going to share my screen. Please let me know when and if it works.
Yes.
Fantastic. Thank you very much. So good morning, good afternoon, everybody. I'm Alex Marshall. I work for Clarke Energy. We're part of Relco, which previously was Kohler Energy. And I'm also delighted to be the Vice President of the CWC. So as a business, Clarke Energy, we're a global business. I was interested to see the map from Simon and some of this overlap between where we operate and where the opportunities are for data centers in general. We're the largest global distributor for INNIO's Yanbacker gas engine business. And I'm pleased that my colleague will be, or my peer at INNIO will be presenting shortly after. I think from a solution provider perspective, it's important not just to talk about energy, is to talk about helping developers to balance the energy trilemma. So energy resilience, or in data centers, the availability of power, cost, and emissions. And by doing those things and setting those in a business context, I think it's important to develop those appropriately for data centers and understanding the needs of data centers. So we as a business also support turnkey EPC capabilities. We're not a manufacturer. And maintenance. If you are running engines base load for a hyperscale data center, their power supplies are the most important things. Therefore, maintenance, correct maintenance is essential in developing an appropriate solution. So as a business, we engineer facilities, we procure and construct them, and then we support after sales support. And then where we operate, I'm just picking up on some of those countries that were mentioned in Simon's presentation. So UK, Ireland, USA, Australia, clearly, but also don't forget other countries, France, Greece, India, and parts of Africa like Nigeria and South Africa. There are data center opportunities in all these locations. So really this market is set to explode, I would say. From a supply option perspective, as a business, we can supply an engine, we can do an engine and EPC wrap, we can wrap a Yanbacker gas engine EPC. We also supply backup gensets in certain parts of the world and service. So getting on to data centers specifically, I'd like to pick up on a couple of things that maybe could be highlighted in the report. There are different types of data center, and each data center has a slightly different use case. Now, we put our first data center project in combined cooling and power and combined heat and power probably 10 years ago. Now, what we're finding, these are enterprise data centers where a business has their own requirements for a data center. It's typically located next to their offices. Historically, many of these installations did not want to put in cooling systems. So they were supplying heat directly to the adjacent building. The interesting one there is Citibank in Riverdale. They developed a combined cooling and power project. So the ability to link the data center with adjacent loads. You then the other data centers that were being developed, a lot of them around 10 years ago now, edge data centers. Some of them, with the advances in chip technology, the chips and the racks that were put in those installations now are slightly obsolete. So if the data center is looking for a refurbishment and they're on a site in a city near to users, London or other areas that are constrained, they then will need significant increases in supply of energy. Now, the grid capacity may only be a certain amount, so retrofitting a CHP or a gas engine to that installation can deliver electricity, cooling, and heat to meet that increase in chip capacity and rack capacity that's needed without them having to move site. And then clearly hyperscalers are the big sexy ones that everybody's talking about that are just on a different level. These facilities, I think, would benefit from a degree of kind of planning in how they're developed, and not just thinking about the data center, but other adjacent users that could use the heat. This was picked up before, but cooling networks, district heating networks. There's a real opportunity there with some joined up thinking to link those two together and get the most type of sustainable energy. The other point to mention, I think it was touched upon, which lithium-ion batteries and engines. So engines are available to operate at fast start, but sometimes the requirements for fast start are in advance of an engine. In that case, you can co-locate or coordinate a lithium-ion battery with a CHP. The lithium-ion battery gives the immediate, very, very fast response times required, and the CHP picks up the load. So hybridizing different technologies should also be thought about. And that's hybridizing electrical systems, that's hybridizing thermal systems. UPSs, standby gas and diesel gensets, the benefits of wind and solar. I think particularly for the hyperscalers, they're playing a little bit of catch up with those types of technologies, but they've got great potential there for those energy solutions. And also, you can also generate, if in a sustainable manner, the gas is close to the site of use as well. So we're talking about renewable hydrogen, renewable biogas, or renewable natural gas, fueling a wholly renewable system. The other point I picked up at a recent data center show was that the operators often don't know exactly the draw of energy at a given point in time. Particularly for the large, the AI data centers, there may be significant peaks and troughs in energy demand at a given point in time. Therefore, hybridizing and flexible generation with different technologies can match the load profile of a particular facility. Now, what we're seeing globally, we've seen installations for the telecom side from a CHP perspective, from the rail side, and also banking data in London with Citibank. Some really exciting projects. We're now then moving into the hyperscale side of things. We've got some fantastic projects under commissioning or construction in Western Europe, over 150 megawatts of capacity. We're seeing orders, engineering orders in the USA, many hundreds of megawatts, and then backup genset supplies for in Australasia, in Auckland, in Adelaide for data center power. So to pick up on some specific opportunities and some specific examples, we have to be a little bit vague on some of these projects as we're not able to talk about huge amounts of detail. But to give an example, we have an early telecommunications project over 10 years ago now in Ireland that's generating electricity and heat close to the site of use to support the operation of the facility. You've got the really pretty green wall that's around the CHP or CCP building at the Citibank project in London. Again, space constrained, next to offices, able to deliver sustainable and more sustainable energy and offset some of the significant costs of running of that data center. And then we have two rail operating centers in Basingstoke and in London with data operations on the site. Smaller installations with that heat recovery. And then we're seeing some of the size and scale of these hyperscale projects with the energy center almost matching the length of the data center itself. Huge installations with backup gensets along with baseload gas, and the ability of gas to also operate flexibly is a real benefit. So this on the right is a 90 megawatt project with 40 megawatts base, 40 flexible, and a built-in redundancy of 10%. So a little bit of repetition, but maybe some slight differences with this Simon's report. So firstly, opportunities, energy efficiency, really matching the energy profile with the sustainable goals of given energy companies, renewable gas generation, integration of other assets to match the benefits of different technologies, given types of systems, the ability to support the grid and give grid interactivity, not just think of it from a self kind of a self perspective, but also thinking about how those assets, if they're not being fully utilized, can support the grid. Integration with district energy, and then finally peak shaving capabilities to reduce costs for a project. And then I think that's largely finished. The other one that hasn't been picked up here is gas engine recips for CHP are alternating current. Other types of power generation are DC, direct current. Data centers often operate on a direct current basis. So hybridization of those systems together can give opportunities for AC-DC microgrids as an is appropriate for a given installation, if that will give technical benefits. So thank you very much for that. I'm happy to either take questions or hand over, depending upon the structure of this next session.
Thank you, Alex. We'll run through the presentations and then we'll have a Q&A session at the end. So just a reminder to all the participants not to forget, if you have a question, to use the Q&A function. Type it in and we'll get to them at the end of the last presentation. So thank you again, Alex. And I'm now very pleased to invite Klaus Payrhuber, who is the Strategic Project Development Manager at the INNIO Group. So Klaus, very happy to have you here with us. And the floor is yours.
Thank you very much, Hans. And hope you can all see my slides.
Yes.
So yeah, good morning, good afternoon, everyone. To this session, I am from INNIO Jenbach, and I will continue this presentation with a short introduction of INNIO and then going to flexible operation of CCHP and CHP, and then showing you some more case studies, as well as talking a little bit about how we get ready for hydrogen. So INNIO Jenbach is from Austria, and this is in the middle of Europe, and we are serving more than 100 countries around the globe. Just to get started, this is our history of our engine development over almost 70 years now. Over a long time, over many decades, we focused on increasing power density and efficiency on our engines. But more recently, the last couple of years, we're focusing much more on operating flexibility and fuel flexibility. In terms of fuel flexibility, going to all different kinds of fuels, sustainable fuels like hydrogen, like ammonia or other e-fuels. And in terms of operating flexibility, to respond to the need of balancing out renewables, where engines provide the backup solution or the balancing solution to fast start and balance out the need of power. We are having a portfolio of engines between 250 kilowatt and 10.6 megawatt. That's the biggest engine. And in terms of application, we have a wide range of application from commercial buildings and utilities and IPPs, which are typically CHP customers, especially in Europe. Then we have data center customers, more emerging data center and microgrid fields. These are newer applications, which is more on the developed side of applications is greenhouses. We're doing several years now, 25 years, I think we do greenhouse applications. And we are a leader in biogas and renewable gases, like landfill gas and sewage gas, as well as special gases like coal mine gas or associated petroleum gas, or even gases from steel mills. So this is our application, a short snap on our applications with our engines. In terms of portfolio, we have offering for 5 types of engines. The smallest engine is the 208 with about 300 kilowatt output. Then we have type 3, 4, and 6. And then we have the big engine with 10 megawatt output. The type 3, 4, and 6 typically come in multiple cylinder versions, 12, 16, and 20 cylinders. But the type 6 has also a 24-cylinder version. And that goes up all the way to 4.5 megawatt. So when we look to our installed base on a global base, then we have more than 40% of our engines installed and running already on renewable gas. Most of them are biogas. And altogether, this represents about 10,000 units they are globally installed. The other 60% are running on fossil gas, typically natural gas. And our task is now to replace these natural gas engines with renewable fuels like biogas or biomethane. And more in the future, it could also be hydrogen or ammonia, for example, and possibly other renewable fuels like e-fuels or synthetic natural gas and so on. The decarbonization is the main topic for power generation at the moment. And when we look to fossil generation, coal is the highest polluting technology, with producing up to or even more than 1,000 grams per kilowatt hour of electricity on CO2. Gas is typically much cleaner than diesel. And at gas, it depends really on the efficiency. You can have a large gas power plant with high efficiency of 60%, but this does not fit everywhere because there's a multiple 100 megawatt gas plants, and distributed generation with gas engine has still a big play. And here, the beauty of distributed power generation on gas engines is that they can produce power and heat because they produce power at the sites where the power is needed, and at the same time they can be placed at locations where the heat is also needed. And CHP units achieve the lowest CO2 emissions around 200 to 225 grams per kilowatt hour. But going much below, we need to change the fuel, switch over to renewable fuels or carbon-free fuels like hydrogen and ammonia. And INNIO is investing in hydrogen and ammonia, those two fuels that are carbon-free, actually carbon-free, not carbon neutral, carbon-free. So looking a little bit at the future of distributed power, including CHP and CCHP, distributed power units based on gas engines are typically installed with multiple units. Yeah, and the multiple unit configuration has big advantages and nice features like the part load efficiency stays more or less constant, more or less over the whole entire range of power output. While when you have a single unit, like a single larger gas turbine, this goes to part load and loses then efficiency. We're also offering a MyPlant remote monitoring system. And with that MyPlant and remote monitoring system and data analytics, we can significantly increase plant reliability. And many of our power plants are operating unmanned. That's also a significant advantage of these solutions. Going forward, we see a lot of different applications for CHP and opportunities for gas engines and CHP. And replacing diesel is actually the first decarbonization step. Replacing diesel means reducing CO2 emissions by about 25%, but also reducing NOx emissions significantly compared to tier 2 diesel emissions. A very easy step to carbon neutral fuel or the carbon neutral power generation is switching the gas to biomethane or renewable natural gas, because then you have physically more or less the same gas, and then you have also you're already carbon neutral. The next step would be hydrogen or ammonia, and then you are having a carbon-free power generation. It's not carbon neutral anymore because there is no carbon. You can really say carbon-free. And all that solutions can be used for data center as well. Here is a concept we developed for data centers based on engines or multiple engines using the waste heat from the engine to run an absorption cooler. And combining power and heat, we can produce the power for the data center as well as the cooling needs for the data center. This is a concept that has been developed and used for several years for many applications, and I will show you a couple of these examples in a minute. In terms of operating flexibility, we invested a lot in fast startup of our engines because our engines can typically start in 5 minutes. That's our standard starting procedure. From pushing the button, standstill engines to full load is 5 minutes is the standard operating procedure. All our engines can optionally start with a fast start capability in 180 seconds, so in 3 minutes. That's an option. And then we have developed one specific engine for data center applications they can start from pushing the button to 100% load in 45 seconds. And with 45 seconds to full load is coming very, very close to diesel capabilities. So that is really the entry step that we can replace diesel backup with gas engine backup solutions. And here I would like to show you a couple examples what we did in the past, more or less in the last 10 years. We have installed, and with our partners, several CHP and CCHP solutions in many applications in several countries around the globe. This is a typical CC application in a hot country that's in Tunisia. And the CCHP is producing power with about 4 megawatt engine in total and cooling of about 3 megawatts. And due to the high efficiency of close to 80% total efficiency, a high fuel utilization rate, the customer is saving a lot of fuel and money in terms of around 50,000 euros a month. And in addition, because this engine is still running on natural gas, they're saving a lot of carbon dioxide. Going to other regions like in China, in Beijing, this is an installation with a CHP technology. And our partners, the local partners in China, they installed 5 620 engines producing about close to 17 megawatt of electricity, using the waste heat from the engine, driving an absorption chiller to produce about 17 megawatt of cooled water. And this is actually for a local data center in Beijing. The total efficiency or fuel utilization rate is very high, is close to 90%. And of course, there is a lot of CO2 emission savings. Another example in Italy, it's an installation of trigeneration for Vodafone Village. And it's not really a data center, but Vodafone is also dealing with a lot of data. And for this village, they have installed a 3 megawatt unit, 3.4 megawatt engine that can produce power, heat, and cooling. That's why it is called trigeneration. It can switch actually from heating to cooling depending on what is needed. Has also a very high fuel utilization rate of close to 90%. And a very similar project to the one in Italy is this one in Karlsruhe at the Institute of Technology. This is a university in Germany that has installed a 2 megawatt engine producing also power and cooling for their local data center. The local data center for the university has also a high fuel utilization rate of around 85%. And finally, as I explained before, we are working on fast start capability, making our engines very close, coming very close to diesel operating capabilities. That was the entry now to larger data centers, standalone data centers. In this case, it is a data center in Ireland. It's our first large data center application with 60 megawatt backup solution. And here, the backup solution replaces diesel engines with gas engines. We supply here 22 Type 6 engines, containerized solution, highly standardized. And of course, this engine can start in 45 seconds to 100% load. So finally, how do we make them ready for hydrogen? And hydrogen we see really as an application for data center. But we see these 3 steps, from diesel to natural gas, and then from natural gas to hydrogen. Natural gas is still a fossil fuel, but it reduces CO2 emissions already by 25% compared to diesel, and it significantly reduces NOx emissions. Going then 100% sustainable, we need to switch over to hydrogen. Alternatively, it could also be ammonia. But going to hydrogen, this would reduce CO2 emissions to zero, and even NOx emissions can be reduced significantly, about 50% and more. We have already an engine that can run on 100% hydrogen. This is our Type 4 engine, and this engine has an output between around 600 kilowatt to 1000 kilowatt. It achieves an electrical efficiency of around 40 or a little bit more than 48%, and the total efficiency is not much different to a natural gas engine. So this engine is available in 3-cylinder versions for the operation of 100% hydrogen. And alternatively, this engine can run on both fuels, natural gas and hydrogen, depending on the availability of fuel. Type 4 is only one type of our engines out of 5, and we're working on the other engines to follow the Type 4 and being able to run on 100% hydrogen. The Type 6 will be offered as the next engine with 100% hydrogen capability. Before we then work on the smaller engines and as well as on the Type 9 to make them 100% hydrogen capable, but this will take more time until we find projects that have enough hydrogen to run a 920 or a multiple 920 engine power plant. So the next one is here. Yeah, this is an example where we installed a hydrogen engine recently. This is a CHP unit in Korea. It's a 60 Hertz application. That engine is a 420 engine, can run on 100% pipeline gas, so natural gas, as well as 100% hydrogen, and has an output of 1060 kilowatt. In this case, it has the same output for natural gas and hydrogen. Typically, the hydrogen output is about 30% lower than the natural gas output of that engine. But what you can also see here on this chart is the NOx emissions. They significantly go down between natural gas operation and hydrogen operation. So when running on 100% hydrogen, this engine is producing less than 50% of the NOx emissions. The hydrogen comes from a polypropylene production as a byproduct, and the engine is installed as a CHP unit, is designed as a CHP unit. It was delivered last year, installed this year, and since a couple of months it is in operation on 100% hydrogen. A very nice project that did go in operation 2 months ago or 3 months ago is this one in Austria. And this is a really demonstration of how to shift renewable power from the summertime to the wintertime. We have oversupply of renewable power on our grid in Austria, and this customer is producing hydrogen with this oversupply of wind and solar in the summertime. The hydrogen is then pumped underground in an empty gas field and stored for winter use. In winter, they take out the hydrogen and run it in a CHP, in a high efficiency CHP, to produce local power and heat. The engine that is installed here is a 412 unit with 530 kilowatt of electric output and 550 kilowatt output of heat. So as winter has started now, this engine is starting to operate this winter. We expect about 2,000 to 3,000 operating hours until spring 2025. And here, our third application with hydrogen, this is a data center. The data center operator North Sea in the Netherlands, they have multiple data centers. It's actually a small data center operator with about 15 local data centers in Netherlands, Germany, and Switzerland. They changed one new data center design for Eindhoven from diesel backup to a hydrogen engine backup. But due to the availability of hydrogen, they have the possibility to run this engine also on natural gas. So they can switch between hydrogen and natural gas, depending on what fuel is available. Biggest challenge is now to have green hydrogen available and at reasonable price with local storage to run these backup solutions. The question before was, do we have experience with fuel cells for data center? This customer has experience with fuel cells as well. Data center Groningen was equipped with fuel cells, but the customer decided to not continue with fuel cells for new data center. They selected our engine, our hydrogen engine, as a backup solution for their new data center. Coming to my last slide, ready for hydrogen. Yes, this is what we offer. All our engines are ready for hydrogen. They can be converted to 100% hydrogen when hydrogen becomes available. All of our engines can cope with some hydrogen in pipeline gas, up to 25 volume%. That's not a problem. And we already offer 100% hydrogen engines today, up to 1 megawatt. And the next engine, up to 4 megawatt, we are offering then next year for bigger projects, but also for a bigger need of hydrogen. So thank you very much. This is what I have today.
Thank you, Klaus. Thank you for your contribution. It's good to hear there are many solutions available to us in terms of decarbonizing CHP, in particular engines. So thank you for your presentation. We'll move on to the third and final speaker, and I'm very pleased to invite Roberto Garcia, who is the Sales Director for the Industrial Segment, Turbo Machinery and Process Solutions from Baker Hughes. So I'm very pleased to invite Roberto to join us. You can turn on your camera and share your screen.
Thank you, Hans. Turning my camera right now. Okay. For some reason, it's not allowing me to share my screen.
I'll ask Mike. Here you go.
Okay. All right. And looks like
everything's working now.
All right. Sounds good. Thank you very much. Thank you for the introduction, Hans. Let me put in a presentation mode. Hey, good morning, good afternoon, everyone. And thank you to the COGEN World Coalition for inviting us. And my name is Roberto Garcia, Director of Business Development, Baker Hughes, specializing in the medium-sized gas turbine applications for industries. And over nearly 25 years, I have been working on developing reliable, sustainable, and cost-effective energy solutions for different industries, and mainly focusing on combined heat and power, CHP applications. So in this presentation, I'm going to be focusing in two theoretical cases. We are working and doing the analysis for data centers. And I have, I believe, 15 minutes, so I'm going to be focusing on the key benefits and expected outcomes. So first, quick introduction of our company. So we have a lot of different turbo machinery technology that we use it on the oil and gas and also in the industrial applications. In this presentation, I'm going to be focusing on gas turbines. We also have some other technologies and solutions, like we are involved in the small modular nuclear solutions. But again, I'm going to be focusing on the gas turbine applications. And we are really committed to the sustainable energy future for the world. And we are doing that in two different ways. So one is our sources of energy. We are looking always to reduce the emissions, to get energy from more sustainable sources, but also we are doing a lot of development and investing a lot of research capital to improve our technology to make it more sustainable and offer it to our customers. So one of the technologies, again, that I'm going to be focusing is our mid-size gas turbines, combustion gas turbines. And just going back to the report that Simon was presented, we all know the challenges that data centers are facing. So one of the big challenges is the lack of grid availability. Again, in some areas, the grid is not going to be available to provide the power needs to data centers on 5 years or 10 years or even 20 years in some other areas. Now, another challenge that data centers are having is due to the AI growth, the size of the data centers is getting bigger and bigger. So with this increase in size of the data centers, they're looking for base power, reliable technologies, and gas turbine is being considered for those bigger sizes data centers. And of course, it is required a technology that has also, it's going to be providing sustainable solutions for data centers. So that will allow the data centers to keep growing. So again, in the two study cases that I'm going to be presenting, I'm going to be focusing on our 16 megawatts gas turbine. That's our Nova LT gas turbine model. And this is a two-shaft gas turbine model. The electrical efficiency is 36%. And the availability of these units is above 98%. And again, some of the main features and advantages that the data centers are seeing for the power and mainly the base load applications is the high availability and the scalable power that they can get from our gas turbines. Also, the compact footprint. In a lot of the data centers, there is a limitation of the footprint that they can use. And also, using footprint for power generation means taking footprint away from the IT buildings. So that's the core business. So footprint is a very important factor for them. And of course, they are looking for sustainable power sources. So emissions is a very important factor. They need low emissions. And the energy efficiency that the waste heat to generate cooling water, it's also something that is starting to be considered for them. The bigger hyperscalers and the collocators are starting to analyze that idea. It is challenging to convince them how this cooling source is going to be helping cooling their IT, and that's something that we all in this industry need to work with them much more in order to show them that this has been used in some other industries for a long time, so it can be applied to data centers. So on this phase study case is under analysis in the US. So the main conditions for this site are the total power is estimated for 75 megawatts. The IT load is going to be around 60 megawatts electric. This location is going to be on a desert conditions. So there is going to be extreme high elevated temperatures and sometimes. And the sources of fuel at that facility is natural gas and diesel as a backup fuel. And in this specific location, the grid is going to be able to provide backup power, not for the full capacity of the data center, but for a good estimated portion of the power. So in this case, the cogeneration will be generating the electricity for the data center, the 100% electricity for data center, and with absorption chillers, there's going to be providing chilled water. It's going to be around 18,000 RTs, and that chilled water will be used for the IT cooling, for the gas turbine air cooling also. And the configuration that it was selected is also based on the availability that this data center requires. So they need to have a tier 3 availability. So for this reason, we define an N+3 configuration redundancy. And as you can see, there is not backup diesel backup power generation defined or included in this configuration. So this high availability is going to be reached by using this N+3 configuration, and the total amount of power are going to be 9 units, 9 gas turbines working with 3 spare engines, and a lot of different operational scenarios has been discussed and evaluated. Some of them having some cold reserve. That means the spare units being down, ready to be operated in case one of the running units shut down. And some other scenarios includes running a certain amount of turbines in addition to the 9, like 11 or 10 units running, and having some spinning reserve available. And in those cases, the response time, in case there is a failure in one of the turbines, is in the matter of seconds. So on the bottom left, as you can see, for example, having some cold reserve units in case there is a shutdown in one of the turbines, then the other turbines will be full speed around 4 minutes after that. Now, in the case of the units running with hot reserve, that means working at partial load, more number of units. For example, 11 units. If there is one unit that is going to be down for any reason, then the recovery time is 12 seconds. If there is a second unit down, then the recovery time is 15 seconds. So again, different scenarios can be provided depending on the availability that they need to have in this data center. And one of the things that doesn't differ from the typical combined heat and power application is that the architecture and the technology of the data center, it needs to be tailor-made for the conditions. It's going to depend on the fuel available, what are the site conditions, the needs of the data center, the response time, the redundancy, etc. So there are a lot of different factors that needs to be considered for this analysis. Now, going to the second study case, also in the US, North America. So in this case, the data center is not going to have available the grid for a long time. So they need to consider base power generation and also backup power. So in this case, for the base load power, gas turbines are being considered, and for the backup power, diesel backup generation is being considered. And one of the things that is also under analysis for the base power, knowing that the grid is not going to be available for a long time, is the gas turbines are going to be running with natural gas at the beginning, and when hydrogen is available at the site and is feasible to use it at the site, then the turbines can take it. The design of our Nobile T16 turbine can use hydrogen without doing any modification to the design, can use up to 20% of hydrogen. And in case more percentage of hydrogen is required, it can be done with some modifications to the turbine. So this is the long-term plan that this data center has for reducing emissions under this specific data center. And in this case, the waste heat is going to be recovered to produce steam and generate more power. So there's one steam turbine that is being considered. So that's a combined cycle. Part of the waste heat is going to be used for for a combined cycle. And also another part of the waste heat is going to be recovered and used for some chilling capacity. And again, that chilling capacity is going to be also used for the IT cooling systems and the gas turbine air inlet cooling, and also for some air conditioner in those in the facilities of the data center and some buildings around the data center. So with this configuration, the level of efficiency is much higher. It's close to the 70% of the whole cycle. The combined cycle portion efficiency is around 48%. And one of the main objectives for this specific customer is to improve the PUE, the power usage effectiveness for this data center. They are looking to reduce it as much as they can. And this configuration, knowing that they don't have the grid available, offers a big improvement. It's close to 50% reduction on of their PUE. So some of the takeaways and conclusions that it is important to evaluate is that first, again, the data center sizes are increasing every day. And for these bigger data center sizes, new technologies needs to be considered. So gas turbines for base power are being considered for, I would say, data centers that are bigger than 50 megawatts, from 50 to up to 300 or 400 megawatts. And again, data centers are looking for improving their PUE numbers, getting close to 1. So in order to reach that, definitely they need to consider the use of combined heat and power for the data centers. Now, again, we mentioned the architecture of the different data center and the power supply for the data centers configuration. It needs to be tailor-made, and the mix of technologies is going to be also something that we are seeing that is going to be very important. So there's going to be different technologies that needs to be also included in those power generation architectures. So that means renewables will be also considered in some of the applications, battery storage, again, fuel cells may be also considered. So a lot of different technologies needs to be included. And another important point is the flexibility. So and mainly for the data centers that does not have the availability of the grid for the few years, maybe 5, 10 years, 20 years, for those data centers, they want to have flexibility on the base load power generation. What I mean by that flexibility, I mean that the source of the energy for those base load applications needs to be also flexible to change, maybe for a peaking application, or to change as a backup application when the grid will be available. So that's something very important that data centers are being analyzed. And there are a lot of challenges to integrate the chilled water into the IT cooling technology. And that's something that I believe we all in this industry, we need to work much more with the data centers to show how these combined heat and power applications and chilled water sources of energy are going to be helping to being more sustainable for their data centers. Now, again, the limited footprint with the data centers increasing in size, footprint, it is an important factor of what technology they need to use. So, and that's a challenge for renewable sources. So solar panels require a lot of footprint. So that's one thing that limited the amount of renewable sources they can use. So again, footprint is an important factor, and of course, in long term, a sustainable source of energy includes also the use of hydrogen. As we all know, hydrogen is not only a CO2-free emission energy source, but also it's a good way to store energy. So that's something that needs to be considered as a long-term solution for data centers. It's probably not ready at this moment due to the economies of the hydrogen, but at some point it's gonna be ready. The technology is gonna be economically feasible and available at the different locations. So it's something that needs to be considered. So with that, I appreciate the time and the attention on this presentation, and open to have further conversations with any people that is interested to learn more.
Thank you, Roberto. Thank you very much for your presentation, particularly the two case studies. Very interesting to see that from your perspective, especially the very large data centers. We have a few minutes for Q&A, so if I can ask the other panelists to join us, turn on your camera, I should say. And of course, Simon and Tom, if you're still there, you're more than welcome to join as well. We did have one question on the Q&A chat function. I'm not sure if anyone is in a position to talk about the maintenance cost per kilowatt hour for large CHP systems. If you want, you can provide a range, but I don't think that's necessary. I have one question, actually, for Roberto, and then after that, if Simon or even Tom, if you have any questions as well, please do chime in. The question for Roberto would be, what do you see are the biggest challenges that you face in the data center evaluations for more energy efficient solutions?
Yes, so I would say probably the biggest challenge is the bigger hyperscalers and collocators. At this moment, I don't think they are fully open to consider combined heat and power as a way to have more sustainable power source. They are still afraid on how the chill water from a CHP application is going to be matching with the IT cooling technology. So we're working in a lot of different evaluations and a lot of different projects with data centers, but again, only few are really considering CHP. I don't know if the other panelists have the same experience, but that's what I'm seeing, and that will be probably the main challenge that I'm seeing.
Okay, maybe Alex, Klaus, do you have anything you want to add from that perspective in terms of main challenges?
No, I mean, I echo the points there. The primary focus on many of these operators is electricity and electricity now. Sustainability is clearly important, but it is possibly not their main driver. And the complexities of integrating CCP is a barrier, although I think as the market matures, they'll realize the benefits of that waste heat.
Thank you, Alex. Klaus?
Yeah, I think I agree with what was said before, and the examples I have shown are rather small data centers, yeah. It can be done, but before the larger big data centers go to integrated solutions, I think there's still some work to do.
Simon?
I'd just like to add one additional question, in that the decision to build a data center and the initial design of that data center is often done before the energy side is considered. So it becomes harder to retrofit things at the 11th hour, maybe it's the 10th hour, but it's still quite late on in the day. So power is fine. They always took power as red, effectively, but the rest of it requires thinking early in the evolution of a data center, not late. And that means that it's much more difficult to get in at that point. And I think what Roberto's seeing in his examples with the bigger data centers, they've already made most of the key decisions. And CHP is just an extra hassle they don't need, even though they do need it, but they don't realize they need it, if you see what I mean.
Maybe a quick comment on that too, what we're seeing in the industry, and I'm sure my colleagues are seeing the same thing. A lot of the big data center people and even the smaller ones are actually going out and securing their own natural gas, for these types of projects. And maybe Roberto or Alex or Klaus, are you seeing that as well? I mean, it's almost a dramatic step change of, people going out, our customers going out and actually buying fuel and securing that so they can look at these types of technologies. Any comments on that?
Yeah, I mean, I can comment that definitely we are seeing that trend. A lot of the big collocators, the hyperscalers, they know that natural gas is going to be needed for the base load with all the restrictions from the grid. So they are focusing on securing the gas, and that will even before the data center size has been defined, even before the technology for the use of that gas is defined. So they're working on that, which that will give security to the projects. Definitely.
Thank you.
Alex?
Yeah, I've got a little question to Klaus and Tom here. On the data center side, the diesel engine manufacturing pipeline is absolutely stuffed with orders from the data center side. The global gas engine manufacturing is less than diesel. And if all of the operators switch from diesel to gas, how are you going to address the demand for those units?
Yeah, that's a good point, Alex. This has been noted, and there's on the other side, there's a lot of promising, in this ramp up. The question is how much will go through and how many will switch to gas. And I think what Tom said before, it is the prime power, and that's why these operators are looking for securing gas supply. So that's really the driver then, and underlining the need and switch to natural gas.
Alex, I would agree. I think we're seeing a demand increase in natural gas, and our diesel demand is so strong as well. So, I guess the answer to that is build a bigger factory. In all seriousness, I think we're going to be seeing an increase in demand for both gas and diesel, to just meet the requirements, because as you're seeing an increase for gas for prime power, a lot of the sites that we're looking at are still potentially looking at putting diesel in for backup, right? So, it just really is becoming a sort of an additive change to our business, which is welcome.
All right. Thank you again. We've just got a few minutes, so let me please just start by thanking everyone for joining us this afternoon, in particular Simon Minette from Shallock Energy. So thank you for your comprehensive presentation. And as I said, we will make the report available in the coming days. If not, at the very latest, next week, we'll be issuing a press release. We'll be publishing the report on the website. Along with this webinar, the recording will be made available, as well as the presentations from the different speakers. So we're looking forward to sharing all this information and getting more information out there about the potential role for CHP when it comes to data centers. Obviously, an exciting and growing market. There's a lot of power demand, and it's not just one technology, and CHP will certainly have an important role to play alongside other technologies in terms of providing that secure, clean and affordable power for these energy hungry data centers. So thank you to all the speakers once again, and thank you for everyone's participation online, and we're looking forward to the next edition of this webinar series, COGEN World Talks. So thank you, and have a pleasant afternoon or evening wherever you are.